Welcome to this course on statistics. This is part A for Unit 1, and I will begin our course on statistics with a discussion of lobotomies. And you may wonder why I'm going to talk about lobotomies if this is a course on statistics, and I'll explain more about that later. So in the 1940s and early 1950s, lobotomies were used to treat many types of mental illness. As mentioned on the screen, you can see about 5,000 lobotomies were performed every year in the United States around that time. And lobotomies were used to treat things that today might be called things like depression and different types of anxiety disorders, or schizophrenia, and sometimes even things like chronic pain, and maybe in a few cases, attention deficit hyperactivity disorder. And the thought was, their theory was, which was a mistaken theory, but their theory was that many types of mental illness are caused by thoughts getting fixed in repetitive loops in the prefrontal cortex of the brain. And they thought that if we could sever some of those connections between neurons in the frontal lobes, it might break these loops and prove to be an effective treatment. And lobotomies were made popular in the United States by a team of two men. There was a neuropsychiatrist named Walter Freeman and a neurosurgeon named James Watts. And they worked together as a team, and they performed lobotomies, and they trained people in how to do lobotomies, and they traveled around the country giving demonstrations on how to do lobotomies, and they helped make lobotomies popular in the United States. And then eventually Freeman broke out on his own, and he developed a procedure that he called his transorbital procedure, and it could be performed with an ice pick as a type of outpatient surgery. And you see on the screen a picture of Walter Freeman performing this transorbital procedure. So at this time in history, an ice pick would have been a common household item that people used to break ice out of ice boxes and refrigerators. And Freeman determined that the skull behind the eye sockets is thin enough that an ice pick could be tapped through it with a hammer. And so what you see happening in the picture here is a procedure where a patient would be first rendered unconscious by an electrical convulsive shock therapy, shock. And then while the patient was unconscious, an ice pick would be placed above the eyeball and then tapped into the brain with a hammer, what you see happening in the picture, and then it would be swiveled back and forth to perform the lobotomy. And then the patient would regain consciousness and sometimes might be sent home later the same day as a kind of outpatient surgery. So today we know this was a terrible, awful procedure. We know it was dangerous and it could cause harmful long-term brain damage in patients. By cutting lesions of the patient's frontal lobes, the procedure caused patients to lose their ability to plan ahead. They lost initiative. They became apathetic. They had problems with inhibition, and they displayed what was sometimes called a mental dullness. Many became unable to care for themselves, and they lived in institutions for the rest of their lives. Occasionally, the procedure caused patients to have seizures or to become paralyzed. So the question here is, why did everyone think it was such a good thing? Because the people believed they were helping patients. They thought it was an effective, useful, good treatment for mental illness. I think the thing that should be especially chilling about the picture you're looking at is the fact that everyone in the picture, they're a group of people who are all well-educated, smart people who want to help and believe they are helping. So how could people who are so well educated and so smart and who so much want to help other people end up doing something so terrible and so awful? How could that happen? And the reason why I raise this question is that I think most of the people taking this class in statistics, if you're taking this class, it means you've had a fair amount of education. You are a smart, educated person. And many people taking a class in statistics and psychology want to help other people. I would imagine most people in one way or another want to be helpful to others in life. And many people taking this course might be wanting to go on into a helping profession or to go on to do psychology research. And many people wanting to do that because you want to be helpful. You want to do good things in the world. So how could smart, intelligent people who desperately want to do good, helpful things in the world end up doing something like a lobotomy that's so terrible? And statistics is going to be a method that we can use to help prevent making these types of terrible, tragic mistakes. So let's look at the story of lobotomies and see what went wrong. What were the mistakes? What were the problems that occurred in this tragic story of lobotomies? And then let's consider the ways that statistics might help us address some of these problems. How can we use statistics to prevent the types of tragic errors that were made in the story of lobotomies? And as we go through this, one thing that's important to keep in mind is that human beings, we naturally have ways of thinking in which we develop beliefs or schemas regarding our ideas about what we think is true in the world and how we think the world works. And once we have these beliefs or these schemas, we naturally, this is something that all people do, we naturally tend to notice the things that fit our beliefs and our schemas. We notice the things that support them, and we naturally fail to notice the things that might contradict our schemas, things that might disprove our schemas. We just naturally don't notice those things. And so we could have used many examples of this. Another example I could have used is the history of bloodletting. So for over 2,000 years, really, in the Western world, common medical practice involved bloodletting. This goes back to the Greeks, the idea that we have these bodily humors like blood, and an imbalance of humors is what was believed to cause illness or sickness. So if someone had some kind of disease, or they were sick, or they had some kind of illness, the idea is you cut the person and drain their blood, maybe use a scalpel and cut them and drain blood out of them, and that's supposed to help heal them and make them better. And we know today that's not helping them at all. If you're draining blood out of a person, that's harming the person. That's not helping them. And not only that, the physicians at this point didn't understand germ theory, and so oftentimes they would not clean their instruments when they went from one patient to the next. So they'd use a scalpel on one patient, and if that patient had some kind of contagious disease, that disease would just get spread from one patient to the next. And so many patients were harmed, and many patients died as a result of bloodletting. And so we can ask the question, how is it that people went, this really was common practice for about 2,000 years. It wasn't ended until really the late 1800s, which wasn't that long ago in history. So how is it that this practice continued for about 2,000 years without people realizing, oh, this is actually harmful and not helpful. We are actually killing people and not saving their lives. How did this get passed down from one generation to the next without people realizing how harmful it was? Well, the answer is because human beings just naturally notice things that confirm our beliefs. So if you think that bloodletting is helpful, if you believe it's a helpful practice, you're going to naturally notice all the times when someone received bloodletting and they seem to get better afterwards. You'll notice those. And you will just naturally not notice the times where maybe someone received bloodletting and they were harmed by it, or they died afterwards, or they got worse afterwards. That's just the way we as humans are made. And that's, in many ways, that can be a helpful thing, because having beliefs and schemas can often allow us to make very efficient and rapid decisions, and sometimes it's good to be able to make efficient, rapid decisions about things. But if you're trying to do scientific observation, that way of thinking doesn't work so well. And so in many ways, what I see statistics as is statistics is a tool that we can use to help counteract this natural tendency we as humans have in the way we perceive things. We're not naturally good at making scientific observations. So let's look at the story of lobotomies. The story actually goes back to this person here, Moniz, who's pictured on the page here. He was actually Portuguese, and he did an initial study on lobotomies in 1935. Originally, he called it a leucotomy, was the term he used initially. And initially, they drilled holes in the side of the head, and they inserted this tool here, I think they called it a leucotome, into the brain, and then twisted it around to do the lobotomy. And we know today this was a very harmful procedure, but he actually won eventually a Nobel Prize for discovering the lobotomy. And his very first report was published in 1935. He had a set of patients that had severe mental illness types of problems, and he did lobotomies, or he called it leucotomies, on each of these patients. And he reported that 7 of these people, after receiving the lobotomy, were completely recovered, which is a rather amazing claim, and 7 were improved somewhat, and 6 were unchanged. And so he's looking at people with severe types of mental illness that are probably destined to spend the rest of their lives in institutions, that they're severely disabled. And so to have some kind of procedure where 7 people are completely recovered, that's an amazing thing. 7 are improved some, and he reports nobody was harmed by this procedure. Some people were unchanged, but most people were helped and got better. 7 completely recovered, nobody harmed. So when you're dealing with something that's as tragic as severe mental illness, this is an amazing, a spectacular result. At one point, I tried to see if I could find the original paper that he published in 1935, translated into English. I couldn't find a version of that, but I did find he actually published another paper 3 years later in 1937, where he reported results from 3 additional cases who received lobotomies, and he reported their results, and I found a copy of that paper translated into English. So let's take a look at some of his results that are reported in that paper and see if we can figure out what went wrong, what happened that led to him to conclude that lobotomies were so wonderful, when in truth they were rather harmful. And here are some excerpts from that paper that Moniz published. So in this paper, he describes 3 cases, or 3 people, and for each person he describes what the person was like, what types of symptoms they were having before he did the lobotomy, or what he called leucotomy procedure, and then he describes what they were like after they received the procedure. So this first case, case 1, initials BVJ, is a female. She was 36 years old. She was depressed. She had a history of suicide attempts, and she was experiencing paranoid delusions. That would be a symptom of schizophrenia, where she's believing things that aren't true. Maybe she thinks people are out to get her or trying to kill her, or has some type of beliefs and some kind of conspiracy ideas where people are trying to persecute her or get her. So she's fairly disabled. And then she receives the leucotomy procedure, and Moniz reports that on the 12th day she felt well, and she said, quote, "It's all over. I've been locked up now for 5.5 years, but I wasn't crazy. I want to go back to live with my daughters." And Moniz reports that she was in good condition, although possibly a little reticent, and he reports that the family found her in excellent condition, just as she had been before the psychosis. And she left the hospital, and now after 6 months, she remains in entirely normal condition. So that's a pretty impressive report. Let's look at the next case. Here we have case 2, initials JRG, a 36-year-old male who was working as a police officer, and then he became agitated, and he also developed paranoid delusions. He was engaging in catatonic behavior. That would be a kind of a movement situation where someone's holding different postures or positions with their body, and they're not moving very much. They might hold a particular posture or position for a long period of time, or they might have kind of a waxy flexibility where if someone puts them in a position, they just stay there and they don't move until someone moves them to a different position. So that would be types of catatonic behavior. And he was also tearing his clothes with his teeth, so engaging in some fairly bizarre types of behavior. And then after the leucotomy, or lobotomy, Moniz reports that after 2 weeks, the patient was in good condition. He talked relevantly and coherently and was correctly oriented, and he desired to go home in order to resume his work. He was observed by Professor Sid. I'm not sure who Professor Sid is. I assume it's someone who's collaborating or working with Moniz, maybe someone else who works maybe at the hospital where he was at or something like that. And Professor Sid considered him well and permitted him to leave. And information obtained recently indicates that he is maintaining his recovery now for 7 months after the operation. So another fairly impressive report. And then let's look at the third case, case number 3, initials JJS, a 36-year-old male, a newsboy. Looks like he had alcohol problems. He was engaging in excessive drinking. He also had paranoid delusions. It looks like he was involved in perpetrating some domestic violence. And he was hearing voices, it'd be hallucinations, would be associated with a diagnosis of schizophrenia. He was unsociable and engaging in odd behavior. And so he looks like he's very disabled. And then after the procedure, after 3 weeks, it was noted that the patient was getting along well, and we were convinced that the hallucinations of hearing had disappeared. That's pretty impressive. We wished to send him to the hospital to be examined by this Professor Sid person, but the patient considered himself cured and he was sent home. And importantly, after 3 months, the patient was altogether well and he had already undertaken his usual occupation. So, another very impressive report. So, the big question at hand here is, what happened? What went wrong? As this crazy bird-like critter is asking. I don't think that's a real bird. I think it's been photoshopped somehow. But anyway, what went wrong? That is, how is it that we had these 3 wonderful glowing reports of people who were incredibly disabled and had these miraculous, fantastic outcomes after receiving lobotomies, when in truth we know that lobotomies are actually very harmful and led to tragic outcomes? What mistake was made here? What went wrong? Well, the first step, if we want to do scientific research, to do scientific investigation, a very first step we need to do is we need to be able to quantify our observations. And when I say quantify observations, I'm going to use the word quantify in a very general term here. So quantify can include both assigning numerical values to people or identifying group membership or assigning people into groups would be another type of quantification. The key thing here, there needs to be some type of systematic way of either assigning people into groups or identifying group membership, or a systematic way of assigning numerical values to people. And note that I can call that quantification, I can call all of that quantification, because if we assign people into groups, I could, if I wanted to, I could use numerical values as labels for my groups. So I could say maybe if I have a treatment group that receives a treatment and a control group that receives no treatment, I could say the treatment group is group 1 and the control group is group 0. It wouldn't, in this case, the numerical values are just labels. They don't mean that one group has more of something and another has less of something. I'm just using the numerical values as labels. So whether I'm using my numerical values just to label groups, or whether I'm using my numerical values to label more or less of something, like maybe I have a scale of depression and some people have higher levels, maybe my scale goes from 1 to 20, and some people have a 14, and some people have a 10, some people have a 4. In that case, my numerical values mean more or less of something. But either way, if I have a systematic way of either assigning or identifying group membership or assigning numerical values to people, I'm going to call all of that, it's going to be called quantification. And note that in the examples we were looking at, there was no quantification. Nobody was being assigned into groups, and there was no numerical values being used to rate people. So for example, let's go back and see. We have, for example, this case 3, where Moniz says patient was altogether well. And things like that. That's just a subjective opinion, but that's not been quantified in any way. That does not assign the patient into a group. That does not give the patient some kind of numerical value. There's been no systematic method of assigning this patient to a group or giving this patient a numerical value. So before we can proceed, now quantification doesn't answer all, that doesn't solve everything just by itself. It's just the first step we need to take in order to start asking and addressing important research questions. So it's just the first step we need to take. Now, once we quantify our observations, that will produce variables. And a variable is essentially anything that varies between persons or cases, whatever we're doing our research study on. So if I say I have a treatment group and a control group, some people are assigned to the treatment group, some people are assigned to the control group, that's a variable because people vary on it. People can be in one group or the other group. Or if I do a study and identify some people as being male and some people as being female, that would be a variable. That would be another two different groups, and people can vary about what group they're in, so that would be a variable. Or if I have a scale measuring how anxious people feel, and the scale goes from 0 to 10, and some people score at 8, and some people score at 4, and some people score at 3, people can have different values on that scale, and so that's a variable. So whenever we quantify observations, the process of quantifying observations produces variables. And for this class, it would be helpful to make a note between two basic types of variables. And actually, I've already been talking about these two types already. One type of variable is called a categorical variable, and the other type is a numerically scaled variable. So the categorical variable, that's the type of variable where the numerical values are just labels for groups. So if I assign people to a treatment group and a control group, if I wanted to, I could label them with numbers. And even if I don't label them with numbers, I'm going to still say I've quantified my observations. I still have group membership. So whether or not I actually assign numerical labels to the groups, that's actually irrelevant. The important thing is if I have two groups, that would be a categorical variable. Or if I have three groups, if I have a treatment group, maybe I have two different treatments and a control group. Now with categorical variables, there's actually two ways that we can get categorical variables and two types of categorical variables. So first, let me mention the two different ways that we can get a categorical variable. So we can get a categorical variable if a researcher assigns people into groups. So that would be the situation, say I have a treatment group and a control group, and the researcher assigns some people to get a treatment and some people to be in a control group that doesn't get a treatment. So in this case, we have differences between people. They're in different groups. And the reason they're in different groups is because the researcher manipulated things and assigned them to be in different groups. And so that would be one way to get a categorical variable, where the researcher assigns people to belong in different groups. Another way we could get a categorical variable is if there's just a naturally occurring category. So if I do a study and maybe I observe some people are, say I look at young adults, and some young adults are in college and some are not. And so I have one group of college students and another group of non-college students, and those would be two different groups, and those would be just naturally occurring groups. The researcher is not assigning people into groups, but I still have groups that people belong to. So we can get categorical variables that might be naturally occurring groups, or that are groups that the researcher creates by assigning people into groups. Either way, we can get a categorical variable. Now, for this class, it'll be useful to distinguish between two different types of categorical variables, which I have on the screen here. We have a dichotomous and not dichotomous. And simply that means dichotomous is any type of categorical variable where there are just two groups, and not dichotomous means there's more than two groups. And this is helpful to note because many types of the data analysis procedures we'll be looking at are things that will use one procedure if it's dichotomous, and we'll need to use a different procedure if it's not dichotomous, if there's more than two groups. Because if there's two groups, things can be simplified in some ways. And if there's more than two groups, the analysis get a little bit more complex. So when we're doing data analysis, we need to make a note of if we have groups, is it just two groups, a dichotomous variable, or not dichotomous if I have more than two groups. So for example, if I do a study and I give people 3 samples of ice cream, I give them a strawberry flavored ice cream and a vanilla flavored ice cream and maybe a garlic pickle flavored ice cream. And I say, pick which one, you have to pick one of these, and maybe I force everyone, you have to pick one as your favorite ice cream, and then whatever one you pick, that's the group you're in, and that way I divide people into 3 groups. So that would be a naturally occurring, not dichotomous example. So for categorical variables, again, we can have categorical variables that are created in 2 ways. Either the researcher assigns people into groups, or we observe naturally occurring groups. And we can have dichotomous variables where there's just 2 groups and no more, or not dichotomous variables where we have more than 2 groups. And then the other type of variable I'll call numerically scaled. And that's where our numbers mean something, where I'm going to rate someone on levels of something. Maybe I look at levels of depression, where a high score means you have more depression and a low score means you have less depression. Or maybe I look at how satisfied people feel in a romantic relationship. And so a high score might mean you have more relationship satisfaction, and a low score means you have less relationship satisfaction. So in this case, high numbers and low numbers mean something. High numbers mean more, and low numbers mean less. Our numbers are not merely labels, but they're telling us amounts of something, and that would be a numerically scaled variable. So again, when we quantify, that produces variables, and it's helpful to keep in mind two basic types of variables: categorical and numerically scaled. Now, when statisticians talk about numerically scaled variables, they sometimes like to be precise and distinguish between three different types of numerically scaled variables, which they call ordinal, interval, and ratio level scales. And so these are all numerically scaled variables, meaning that higher numbers mean you have more of something and lower numbers mean you have less of something. Now, with an ordinal level scale, it means that and not much else. And so with an ordinal level scale, the distances between the units on your scale are not necessarily even, not because you're intentionally trying to make it jumbled up, it's just that you don't have a way to measure precisely. So you might have a scale where maybe here's my scale measuring, say, how happy people are, and this mark here, this might represent a 1 on my scale. Maybe have a scale going from high to low here, make a kind of a number line here, going from high to low, and maybe this is a 1, and maybe right here this is going to be a 2, and then maybe here that'll be about a 3, and then maybe 4 is going to be right here, and maybe there's a 5 and a 6, 7, 8, 9, and maybe 10 is right here. So the thing to note is that my units are not evenly spaced. And this would be the type of thing that maybe I have a 10-point scale, and when people use my scale, that going from a 1 or 2, that represents about this much increase in happiness, and someone going from a 2 to 3 represents that much increase in happiness. It's not that I've intentionally tried to make uneven units, it's just that I'm measuring something that's rather complex and arbitrary, and it's hard to know, is going from a 2 to 3 this much, or is it twice as much? And so with this type of scale, I can't say that someone who has a 4 has half as much happiness as someone who has an 8, or that an 8 is twice as much as a 4, because my units are all unevenly spaced. And this is actually true for most of the things we assess in psychology and neuroscience are like this. We can't assess with a level of precision that tells us for certain that all of our units are evenly spaced. In psychology and neuroscience, most of what we are assessing are constructs that are rather abstract. We want to assess something like pain or depression or happiness or satisfaction, and these are things that we can't measure with perfectly evenly spaced units because there's no way to define perfectly evenly spaced units. So most of the things we assess in psychology and neuroscience are actually assessed with ordinal level of scales. Now, an interval scale is where you have evenly spaced units. So if I have a scale where everything is evenly spaced, I'll try to make it as evenly spaced as I can. So if these marks were, note here it's close to even, but technically this is still ordinal because I'm just drawing this and these aren't perfectly evenly spaced. But if it was evenly spaced, that would make it an interval level scale. So an ordinal scale, the distances between my units are not evenly spaced. Going from a 1 to a 2 is not necessarily the same as going from a 2 to a 3. An interval level scale is where all the units are evenly spaced. And then a ratio level scale is where you have a meaningful 0. If you have like a point to 0, and 0 actually means the absence of something. So if you have a 0 on your scale and 0 means 0, nothing, then it's a ratio level scale. So ordinal is where the units are not necessarily evenly spaced. Interval is where the units are evenly spaced, but there's not necessarily a meaningful 0 on your scale. 0 doesn't necessarily mean the absence of anything. And if you have evenly spaced units and you have a meaningful 0, that's a ratio level scale. So like I said, the very first step in doing scientific research is we need to quantify our observations. And if we don't quantify our observations, then we can't even begin to answer important research questions. But once we quantify our observations, we assign people into groups or identify groups, or we assign numerical values to people. Once we quantify our observations, at that point we can start taking steps towards addressing important research questions. So let's consider this. What would have happened if Moniz had quantified his observations in his research on the effects of lobotomies? Here's one example of a way that observations could be quantified. On the screen is an instrument called the Brief Psychiatric Rating Scale. So this is an instrument that a researcher or a healthcare worker could use, where the researcher or healthcare worker interviews a client or a patient, and then after the interview rates the patient on several different levels. So for example, to what extent does this person display hostility? And then you rate 0 means not present, 1 very mild, 2, 3 up to 6 extreme. And note that the scale here, 0, 1, 2, 3, 4, 5, 6, that's an ordinal level scale going from not present to very mild. We don't know that that's an equal distance going from a very mild to mild. We don't know that's an equal distance going from 2 to 3. So this would be an ordinal level scale, but it would be quantifying the observations. It's a numerically scaled variable. And actually how this one works is that the clinician or researcher makes ratings on all of these different symptoms. So rate, for example, hallucinations, 0 to 6, uncooperativeness, 0 to 6, going all these things, guilt feelings, tension, all these unusual mannerisms. So every single symptom gets rated on a scale of 0 to 6, and then all these values get added up together to produce a total score on this brief psychiatric rating scale. And so that would be one way that symptoms could be quantified. This would be a numerically scaled quantification of symptoms. And this would be something that, say, we did a study on lobotomies and we had patients that received the lobotomies. Instead of just making these subjective reports that say, oh, the patient's doing wonderfully, we could have the patients assessed using the brief psychiatric rating scale, and then every patient would receive a score on the brief psychiatric rating scale, and at that point, their observation would be quantified. Now, this isn't going to solve everything. It just means once we've quantified the observation, now we can address some important questions. So what if Moniz had administered the brief psychiatric rating scale to the patients in his study? If he had quantified his observations, what questions could we address? As this happy platypus is wondering here, what questions could we address if we quantified the observations? At least I think that's a happy platypus. I don't know how to read platypus emotions that well, but I assume that platypus is happy and the platypus is wondering, what questions could we address? So if Moniz had administered the brief psychiatric rating scale, as I mentioned, the scale works where a clinician or a researcher interviews a patient or a participant in a study, and after this interview, the researcher or clinician rates the patient on several different symptoms, and then those scores get added together to get a total score. And total scores on the brief psychiatric rating scale can range from 0 to 108. And in samples and studies where they've had clinical populations, meaning people that fit various diagnostic categories, the average or the mean score is 24 and the standard deviation is 11. We'll be talking about means and standard deviations shortly here. So if you know what that means, that can mean something to you. And if you don't know what that means, we'll be talking about that in just a moment. So that's the brief psychiatric rating scale. And let's just imagine, say Moniz gave this scale to the three cases, case 1, and just say, for example, case 1 got a score of 27 on the brief psychiatric rating scale, and case 2 got a score of 36 on the brief psychiatric rating scale, and case 3 got a score of 54. So if that was a scenario, if these three cases got these scores on the brief psychiatric rating scale, what are the important questions we could address at this point now that our observations have been quantified? So one of the very first questions we might want to address, seems like a relatively simple question, is simply this: are these scores high or low? And how do you decide? So I've got a 27 and a 36 and a 54. Are these all high scores? Are these all low scores? Or, 27 is lower than 54. Maybe 27 is a really, really low score and 54 is a really, really high score. Or maybe they're all low or maybe they're all high. And if you think about it, it's a rather tricky thing to figure out. And this is something we often want to do in research and maybe in life in general, is to be aware of what things are high and what things are low, what things are extreme and moderate and low. We often need to be able to rate things. And when we rate things, we need to decide what's high and what's low. But how do we go about deciding what we should call high and what we should call low? And that's one thing that we'll be looking at later on in this course. We'll look at methods we can use for determining what constitutes a high score and what constitutes a low score. For now, keep this question in mind, and note this is an important question and a question we will be talking about how we can address later on. And maybe you can be pondering yourself of how would you go about addressing this question. Maybe you can even guess what we're going to do, a method that we might use to determine are these scores high or low. Other important questions that we would want to address if Moniz had quantified his observations are questions of reliability and validity. And the issues of reliability and validity are often considered together, and you may have talked about these issues in previous courses. And if so, you might want to take a moment and recall what is the definition of reliability and what is the definition of validity. So I have on the screen here actually my definition of reliability, and reliability in general is going to have to do with consistency in measurement. Or to say it in more precise terms, you have good reliability when the same amount of something always produces the same assessed numerical value regardless of when or how it is assessed. Every time you assess the same thing, you get the exact same numerical value, and that would be reliability. Let's contrast that with validity. I'll go to my next slide, and here I have the definition for validity is simply the scale measures what it is supposed to measure. So if I want to measure statistical knowledge and I give you a bunch of, say I give you a bunch of jelly beans and ask you to sniff the jelly beans and recognize the flavors of the jelly beans and use your jelly bean flavor recognition score, and I think I'm measuring statistical knowledge, if I give you a test in stats and I ask you to sniff jelly beans, that's probably not a valid measure of statistical knowledge. I'm measuring something different. I'm measuring your jelly bean sniffing ability, not measuring your statistical knowledge. And so in that case, my scale would have poor validity. Or say I have my pet happy platypus, and I put my platypus on a scale to see how heavy my platypus is. And let's consider a couple scenarios and see what is reliability and what is validity. So say I put my platypus on the scale. I don't know how much platypuses actually weigh, but say I put it on the scale and I get a reading of 12 pounds. And then say I put my platypus on the scale again, and this time it says 15 pounds. And then I put my platypus on the scale, and next time it says 8 pounds. And then I put my platypus on the scale, and then it says 20 pounds. So each time I put my platypus on the scale, I'm getting a different value. So is that reliability or is that validity? Which issue am I illustrating? And that would be a lack of reliability. Every time I assess my platypus, I'm getting a different value. So I'll go back to my previous slide here. Here's reliability. That would be a situation where the same amount of something, my platypus is not changing how much it weighs, so the platypus's weight is staying the same amount of something. In that example was not producing the same assessed numerical value. Every time I put my platypus on the scale, I was getting a different value. So that's an example of lack of reliability. Now, what if I put my platypus on the scale and it says my platypus weighs 120 pounds? I don't think my platypus weighs 120 pounds. So I put my platypus on the scale again and I get 120 pounds. And I put it on again and it says 120 pounds. Every time I put my platypus on the scale, it says a platypus weighs 120 pounds. Now that would be highly reliable. I'm getting the same exact value every time I assess my platypus, but 120 pounds is not what that platypus weighs. So this would be an issue of validity. Go back to that validity slide. That is, a scale is not measuring what it's supposed to measure. 120 pounds is not what my platypus weighs. I don't know where that number came from, but it's not my platypus's weight. So if my scale is consistently telling me 120 pounds, it could be highly consistent and have good reliability, but terrible validity. Or here's another example. Maybe I wanted to assess, say, how depressed someone was, or I had a sample of people and I wanted to assess depression in the sample of people. and I told each person, please write down the last 2 digits of your social security number. And I just took that as your index of depression. So if you had a high value, I assume you're more depressed. And if you have a low value, I assume you're less depressed. And then say I had people come back a few days later and I said, let's do the same thing again. I'm going to assess your depression. Please write down the last 2 digits of your social security number. And they wrote it down and I looked at that. And then maybe I did it a few days later and said, please write down the last 2 digits of your social security number. And note that every time, for the most part, people are writing down the exact same number. And so I would say that's a highly reliable way to assess depression. But that method has absolutely zero validity. I'm not assessing depression at all. I'm assessing their social security number. So I'm getting values that have no validity, but they would have high reliability. And so they're 2 separate constructs. Reliability has to do with the stability of measurement, and validity has to do with, is your scale measuring what you're supposed to measure? Let's go back to my reliability slide here. And I want to note that in psychology and neuroscience, just about everything we assess is actually never going to have perfect reliability or perfect validity. So the issues of reliability and validity are not something that an instrument either has or doesn't have reliability or validity, but these are issues we need to talk in terms of amount. To what extent is an instrument reliable, and to what extent is it valid? Because the things we assess in psychology and neuroscience are often very complex, abstract constructs that have somewhat arbitrary measurement scales and are difficult to assess. And there's almost nothing I can think of that we could assess. I suppose if I assess someone's age and I say, how old are you in terms of years, I could probably get that fairly, maybe I get the same age every time. So there's probably a few things that I could assess with very high, near perfect reliability. But the vast majority of stuff we want to assess is not going to have perfect reliability. Now, when you think about reliability, one way to think about this, I often think about that there's a Dr. Seuss book that I think it's The Green Eggs and Ham. It talks about, Sam, I am, do you like green eggs and ham? And he says, no, I don't. He says, the question is, would you like it in a house? Would you like it with a mouse? Would you like it on a train? Would you like it in the rain? And so forth. The book goes like that. And I think that book helps give an illustration of reliability, because we could say, if I want to assess you, say I'm going to assess how, say, someone's relationship satisfaction, how happy a person is in a relationship. I could say, what value do I get if I assess you on a train? What value do I get if I assess you in the rain? What value do I get if I assess you in a house? What value do I get if I assess you with a mouse? And we can think about, if I want to assess something like relationship satisfaction, we could say there's an infinite number of ways I could assess that. That if I have a questionnaire, I could have an infinite number of possible items I might put on that questionnaire. So do I get the same value if I use this set of items or if I use that set of items? And if I want to assess someone's relationship satisfaction, if it's not changing over time, I could assess it at a different time. I could assess you in the morning. I could assess you in the afternoon. I could assess you today or tomorrow or the next day, assuming that your satisfaction isn't changing. I could assess you across many different times. And do I get the same value every time I assess you? Or I could assess you in different locations. I could assess you maybe in a classroom on a college campus. I could have you, maybe you could do it at home online, go on the computer online at your house, and I could assess your satisfaction there. Or maybe I could assess your satisfaction as you're traveling in a car or an airplane or a train. Or I could assess you outdoors. I could assess you maybe when there's some kind of distraction going on, or maybe I could assess you in a very quiet place. So there's all different places I could assess you. And every time I assess someone's satisfaction, even though their satisfaction could be the same every time, I'm probably going to get a different numerical value. And that's an illustration of a lack of reliability. And in research, nothing we assess is going to have, just about nothing, maybe there's a few things, but just about nothing we assess is going to have perfect reliability. So the question is always a question of, to what extent does a measure have reliability? And the way that we test reliability is usually by looking at correlations between different assessments. So if we go back to our example of Professor the Moniz and his lobotomies and his Professor Sid, one thing we could do is say, what if Moniz administered the brief psychiatric rating scale and got scores on his 3 patients. And then what if this Professor Sid person, I forget whoever that was, that Professor Sid, what if Professor Sid also administered that brief psychiatric rating scale and gave his ratings? So we had the scores for each patient based on, jumping around there. We have the scores based on Moniz, and we have the scores based on Professor Sid, and we can see what's the correlation between these 2 scores. You see, they're not exactly the same. Each person is giving a slightly different score. Although in this case, this example looks like they both, this case 1 was given kind of a low score, at least compared to case 3, although Sid rated case 2 the lowest and Moniz rated case 1 the lowest. So they're kind of related, but not perfectly related. So we could look at the correlation between these 2 scores to give us an index of to what extent are these ratings reliable. And we'll be talking more about reliability and specifically how we can give ratings of reliability later in this class. So one key question has to do with reliability. And whenever we do research in psychology and neuroscience, this is always going to be an important question because the scales we use are almost never going to have perfect reliability. So we'll always want to know to what extent are our scales reliable. And so that's the question of reliability. Then the other question is the question of validity. And the question with validity is often a question we address by saying, okay, here's what I intend to measure. If I'm measuring what I claim to be measuring, what types of things should it correlate with? How should it perform if I do some research study and see what it's related to and what it's not supposed to be related to? So, for example, is a score on the brief psychiatric rating scale actually measuring the type of symptoms and psychological distress that it's supposed to be measuring, or is it measuring something else? And for example, I might say, well, if it's measuring what it's supposed to be measuring, I think it should be related to how many days in a year a person works. That is, if they're experiencing lots of symptoms, that should make it hard for that person to work, and they might work fewer days. And if they have fewer symptoms, that would enable the person to go back to work and to work many days at work. So I could think, I could say that if my scale is valid, if I'm really measuring how much someone's disabled and someone's level of symptomology, that those symptoms should be correlated with how many days a person works in a year. So we could do a study where, say, Moniz gives his ratings, say this person got a 27, that person got a 36, that person got a 54. Moniz gives his ratings, and then maybe we observe those people for a year and get some kind of index of how many days over the year did the person work. So if case 1 worked 125 days, case 2 worked only 10 days, case 3 worked 20, they didn't work very much. And then we could see what the correlation is, and that can give us an index of to what degree are these scales measuring what they're supposed to be measuring. So with validity, we consider what are these scales supposed to be measuring, and if they're measuring what they're supposed to be measuring, what should they correlate with? And then we do a study to see if they correlate with the things that they're supposed to correlate with. And that's how we would address validity. So that's how we would address both the questions of reliability and validity, and these are 2 key questions to address in doing research. And we'll be talking about these issues later on in this class as well. We'll be talking a little bit about them later on in this class. And if we go back to that question, what went wrong in that research that led to the conclusions that lobotomies produced wonderful outcomes? What went wrong in that research? Well, one of the key things that went wrong had to do with the issue of validity, the issue we've just been talking about. Because if you think about Moniz's assessments, how he was giving those subjective reports of his patients' outcomes, and he described them as having wonderful outcomes and as returning back to their normal ways of life. Well, those assessments probably lacked validity. He was probably exaggerating positive things and ignoring negative things. He was not measuring the thing that his assessment was supposed to measure, but instead he was measuring the thing that he wanted to see, his own beliefs and ideas about what he hoped his patients were experiencing, and not what they were actually experiencing. And if he had quantified his observations and produced a scale that had numerical values on it, he could have then done a test to see how valid his observations were. He could have looked to see how well his observations correlated with the things they were supposed to correlate with. And if he did that, he would have discovered that his observations, his scales, his assessments had terrible validity. And that was one of the key things that went wrong in that line of research. So in considering the different types of questions we could address, if Moniz had administered the brief psychiatric rating scale and quantified his observations, we can make a distinction between two general types of research. One type is called correlational research, and the other type is called experimental research. Now, recall when I was talking about types of variables, I mentioned two different ways that a variable could be created. So one thing that could happen is that a researcher could create a variable by assigning people or cases. It could be people or rats or animals or corn plants or whatever the researcher is studying. But the researcher assigns cases into groups. Maybe there's a treatment group that receives some kind of treatment and a control group that receives no treatment. And if we have a treatment group and a control group, then we have a variable which is called group membership, and people's scores on that variable are what group you're in. You're either in the treatment group and a control group, and those scores are determined by the research. The researcher determines what group you're in. That means the researcher is determining people's scores on the variable. The researcher is randomly assigning some people to get the treatment and randomly assigning other people not to get the treatment. Whether or not you get that treatment is your score on that group membership variable, and your score was determined by the researcher. So when the researcher determines people's scores, I call that a manipulated variable. A manipulated variable is where a researcher assigns people into groups, and people's group membership is determined by the researcher. The other way to get a variable, and probably the more common way to get a variable, is where we simply assess it. People or corn plants or rats or whatever we're studying, our cases are assessed. And we might assess our cases and determine what group they naturally belong to, or we might assess cases and determine their scores on a numerically scaled variable. Either way, we're assessing our cases and then determining their scores based on our assessment. So we could assess cases and determine what group they belong to. Maybe we could determine whether they identify themselves as male or female, or whether they are college students or non-college students. Those would be categorical variables that we could assess. Or we could assess their scale on a numerically scaled variable, like levels of depression, or levels of pain, or levels of happiness, or levels of relationship satisfaction. Now, in general, a manipulated variable will always be a categorical variable. It will be a researcher assigning people into groups. It could be just two groups, or it could be 3 or 4 or any number of groups. But a manipulated variable is always categorical. In contrast, an assessment is something that could produce a categorical variable, or it could produce a numerically scaled variable, either way. So with this in mind, with this distinction between an assessed variable, that is a variable that's determined by an assessment, and a manipulated variable, which is a variable that's determined by the researcher, we can now use this distinction to clarify the difference between correlational research and experimental research. And essentially, correlational research is going to be research where all the variables are determined by an assessment and nothing is manipulated. In contrast, experimental research is going to have at least one variable that is manipulated. So let's start by taking a look at correlational research. So in correlational research, here's a definition for correlational research. It's a study where scores for all the variables are determined by an assessment and there are no manipulated variables. So that would be correlational research. So the distinction between correlational and experimental research essentially boils down to this. Was there manipulation? If a researcher created a variable by manipulation, if a researcher assigned people or cases into groups, if group membership was determined by the researcher, well then it's experimental research. In contrast, if there's no manipulation, if the researcher did not assign cases into groups, well then it's correlational research. And notably, this terminology can be a little bit misleading. because whether or not something is correlational research actually has nothing to do whatsoever with whether or not a correlation is calculated in the study. Because we can do experimental research and calculate correlations, and we could do correlational research and not calculate any correlations. I think this terminology goes back to a point in history when probably most people that were doing experimental research didn't realize that they could calculate correlations if they wanted to, and most people doing correlational research were probably calculating quite a few correlations. And so this terminology made sense at one point in history. But for better or worse, it's still the terminology we use today. So correlational research does not mean that you're calculating correlations. It simply means it's a study where there's been no manipulation. The researcher did not assign people into groups. So here's an example. See if you can figure out, would this be correlational or experimental research? Say I did a study and I was wanting to treat psychological distress. And let's see, the study of lobotomies is kind of traumatic here. Let's think of something a little more lighthearted. Say I had platypus therapy, kind of like a pet therapy where I had people spend time with a happy platypus to see if that would make them feel better. So I got a sample of people. Maybe I get a sample of 60 people, and these are all people that are experiencing some kind of distress in their life. And I have them go through 4 weeks of platypus therapy where they spend time with a platypus. And I do my study like this. At the beginning of the study, before they start therapy, everyone takes the brief psychiatric rating scale. So I give that brief psychiatric rating scale, and everyone gets a score on the brief psychiatric rating scale before the study begins. And then everyone gets, say, 4 weeks of platypus therapy where they get the platypus therapy and spend time with the platypus. And then at the end of that treatment, everyone takes that brief psychiatric scale a second time. So I'll call it T1, was their assessment on the brief psychiatric rating scale prior to the treatment. And then they get 4 weeks of treatment. And then after the treatment, time 2, they get assessed on that brief psychiatric rating scale a second time. And I want to see, do scores improve? And maybe my study finds that actually scores improved, that scores at time 1, people were very distressed, and at time 2, they were less distressed, and there was improvement over time. So the question is this study that I'm describing here, is this correlational research or is this experimental research? Well, the answer is it's correlational research. I did not assign people into groups. There was no group membership that was determined by the researcher. In this case, everyone got the treatment. This type of study is something I would call a difference score study. And a difference score is I'm looking at the difference between your score at time 1 and your score at time 2. I want to see, is there a difference? Is your times 2 score different from time 1? So I'll call this type of study a difference score study. And a difference score study is a type of study that's a type of correlational research because I'm not manipulating a variable. I'm not determining what groups people belong to. Now, one key limitation, anytime you do correlational research, one limitation of correlational research is that this type of research cannot really tell us information about cause and effect. So if I find that people improve over time, I cannot conclude that my platypus therapy caused that treatment. There could be many other things that might cause people to improve over time. For one main thing is that oftentimes when people sign up for treatment studies, they seek treatment at a point in their life when they're feeling especially distressed. And distress is something that naturally goes up and down over time. And so if people seek treatment at the time when they're feeling most distressed, chances are, if you come back a month later, they're going to be feeling a little bit better because distress goes up and down naturally. And so if distress, here we go up and down naturally. Here we go, the ups and downs of distress. And people usually seek treatment right here at a low point when they're feeling really, really distressed. And over time, their distress is probably going to get a little bit better. So if we just wait a few weeks, if you're feeling really, really bad, you're feeling the worst you've ever felt in your life right now, chances are a few weeks from now, you'll be feeling a little bit better. And so people can improve just with the passage of time. And this is going to be true for all types of correlational research. When there's no manipulation, that means we're limited in being able to determine cause and effect. We cannot really use correlational research to draw conclusions about which variable is causing which outcome. Now, that's not to say that correlational research is bad, because correlational research does have some important advantages. There are some things that it's really good at doing. One thing that correlational research is really good at doing is helping us understand the way things naturally occur in the real world. Because I'm not manipulating, I'm not changing anything, so I can see how things naturally occur in the real world. I have a note here that includes research on process and etiology. So process, I'm thinking of one type of research that's sometimes called process research, where it's in a clinical setting where you're doing different treatments. Like say you're looking at different types of psychotherapy. Maybe you're looking at cognitive behavioral psychotherapy, or you're looking at maybe some kind of psychodynamic types of psychotherapy, and looking at how these different types of psychotherapy lead to outcomes in people. And process research is research where they look at what type of process occurring during the therapy is correlated with what types of outcomes. So for example, if there's a strong alliance between the therapist and the client, does that correlate with positive outcomes? Or if the therapist makes a lot of statements, maybe the therapist makes a lot of statements that reflect the client's feelings. If there's a lot of reflective statements where the therapist reflects the client's feelings, are those reflective statements correlated with positive outcomes? So process research is a type of correlational research where researchers look at what types of processes occurring during therapy correlate with outcomes after therapy. And that's something that you couldn't really study that with an experimental study. That's a type of process research that would use a correlational design. Or research on etiology. So etiology are what are the causes of disorders. So if you're looking at something like depression or an anxiety disorder, if you're looking at some kind of disorder and want to know what causes that disorder, what are the things that cause people to develop that order, that's a question of etiology. So questions of etiology are questions of what are the things that cause people to experience different disorders. And you can't do a research study where you assign people, for example, if you think that maybe having an abusive parent might cause someone to experience a negative outcome later in life. Well, you can't do a study where you randomly assign some people to experience abusive parents and other people don't experience abusive parents. Partly because that simply wouldn't be ethical. But even if you could, if you randomly assign some people to experience abusive parents, it probably wouldn't be the way abuse naturally occurs in the real world. So you'd be studying kind of an artificial abuse and not a real abuse. So there's not really a way that you could do an experiment. It would be hard to use experimental research to study etiology. So if you want to understand ways that things naturally occur in the real world, then correlational research is usually the best way to go. But if you're wanting to understand cause and effect, if you want to determine, is this treatment, I have a treatment, I want to determine, is this treatment effective? Will this treatment cause people to get better? That's a question of cause and effect. And that type of question is not well addressed with correlational research. So correlational research is effective and a good type to use when you want to understand the way things naturally occur in the real world. But if you have a treatment and want to understand, is your treatment effective, and want to address questions of cause and effect, then correlational research is not the best research to use. And here is my definition of experimental research. And as I mentioned, the key thing that makes something an experimental study is when you have at least one variable that's created by manipulation. Now, in experimental research, you will also have variables that are created by an assessment. So you'll have both types. So an experimental research is a study that has at least one variable with scores determined by an assessment and at least one manipulated variable that's produced by the researcher forcing cases into groups. So we have to have at least one variable where group membership is determined by the researcher. So you might have the researcher assign people into a treatment group and a control group, and then maybe look for levels of happiness, maybe between those two groups, to see if the group receiving a treatment is happier than a control group that receives no treatment. So in this case, you'd have one variable that's determined by the researcher, that manipulated variable produced by the researcher forcing people into groups. That's the group membership variable. Are you in the treatment group or the control group? And you have one variable with scores that are determined by an assessment. So that would be the level of happiness maybe that people experience at the end of the treatment. So if you give a treatment, you assign people to a treatment group and a control group, and then assess their level of happiness at the end of the treatment. The group membership was assigned by the researcher. That's the manipulated variable. The level of happiness was determined by an assessment. That's the variable that was assessed. And that would be an experimental design. In that case, it has one variable determined by an assessment and one determined by the researcher, forcing people into groups. So the key thing that makes something experimental research is there has to be some form of manipulation. That is, the researcher has to assign cases into groups in order for it to be experimental research. And one particular type of experimental research is something called a clinical trial. And a clinical trial is simply when we use experimental research to test the effectiveness of some treatment. So the treatment could be maybe it's a new drug, or maybe it's a vaccine, or maybe it's a new type of psychotherapy. And so we conduct experimental research to test the effectiveness of our treatment. And if we do that, we call that a clinical trial. So in a clinical trial, you get people, maybe if it's a treatment for depression, you would get a sample of people who are depressed. Or you get a sample of people who are at risk for whatever outcome you're trying to treat. So if the treatment for depression, say, we get people who are depressed, and some people are randomly assigned into a treatment group and they receive our treatment, and other people are randomly assigned into a control group, and the people in the control group do not get our treatment. And then after the people in the treatment group have received their treatment, afterwards, we assess people on the outcome. And it's whatever outcome we're trying to treat. So if it's a treatment for depression, we'd assess people on levels of depression at the end of the study. But the OUT outcome. We assess their outcome at the end of the study. There we go, outcome. And we see if there's a difference between the two treatment so we have one variable, it's our group variable, and this our grouping variables, whether or not you're the treatment group or the control group, and that's the one that's determined by the researcher. The researcher assigns people to be either in the treatment group or the control group, and that's a dichotomous categorical variable about what group you're in. Our outcome variable is going to be usually a numerically scaled variable, say levels of depression, or maybe if you're testing a vaccine, it would simply be the number of people that are either get the disease or don't get the disease you're trying to vaccinate for. And so we see if there's a difference between those two groups in levels on this outcome variable. And when we do that, that's called a clinical trial. So a clinical trial is simply when you do experimental research to test the effectiveness of a treatment. Now, one thing that's important, when you do experimental research, the researcher needs to use random assignment to put people into groups. So whether or not you're, say, in the treatment group or the control group, that needs to be determined by random assignment. So if the researcher had people come into a study and say, well, the people I like, they're going to go into the treatment group, and the people that I don't like, they're going to go into the control group, well, that's not random assignment, and if a researcher did that, it would not be a valid study. Or if the researcher had people come in and the researcher said, well, here's what the treatment will be like. Do you want to receive the treatment or not? And the people who chose the treatment would get the treatment, and the ones that opted out of it would not get it. And people chose which group they're in. And if people get to choose which group they're in, well, then it's not random assignment. It's not an experiment anymore. So in order to have a valid experiment, the group membership needs to be determined by random assignment. The researcher needs to determine it, and the researcher needs to use random assignment as a process for determining group membership. Now, like I've said, I talked about the limitations and the advantages of correlational research. Recall that for correlational research, one advantage was it was particularly useful for understanding how things naturally occur in the world. And a key limitation of correlational research was that it was not good for determining cause and effect. Well, the exact opposite is true here. So a key strength of experimental research is that if you do it properly, you can make valid statements about cause and effect. So if I do this clinical trial and I assign some people to my treatment group and some people to my control group, and I determine afterwards there's a significant difference between these two groups in the outcome, I can conclude that my treatment was responsible for causing that difference in the outcome. So a key strength of experimental research is that we can make conclusions about cause and effect. Now, the converse side is the limitation is that there's a limitation. It's not really good for explaining natural phenomena. And the key thing is there, when you do experimental research, you're manipulating something, you're intervening into the natural world. And so you're, by the nature of what you're doing, you're not studying something natural. You're studying something that you've created by your manipulation. So if you want to understand, say, what are the natural causes of some outcome, maybe you wanted to understand causes of cancer. Well, you can't say, if I had, maybe I think that smoking causes cancer. I can't do a study where I manipulate people and assign some people to become, let's say, this group of babies, they're going to grow up and become smokers, and this other group of babies, they're going to grow up and not smoke. Again, it's not ethical to do that. I'm not sure I could do it. And even if I could do it, it probably wouldn't be the natural way that people smoke, and so I'm not sure I'd be studying the way that smoking actually affects things anyway. Or if I wanted to, like for example, a lot of my own research, sometimes I've done studies looking at interpersonal relationships and say romantic relationships and couples, and what makes couples feel happy and satisfied. And for example, one thing, maybe I have a theory that if one partner blames the other partner and thinks the other partner's having an affair, that if I think my partner's having an affair, that would probably lead to a negative outcome in the relationship. I'd probably feel distressed in my relationship. So my theory is that one partner believing the other is having an affair leads to relationship distress. Well, I can't manipulate that. I can't do a study where I get a sample of couples and randomly assign some couples to believe their partners are having affairs and randomly assign other couples to not believe their partners are having affairs. Again, it's something that it wouldn't be ethical to manipulate even if I could, and I don't think I can manipulate it. And even if I could manipulate that, I wouldn't be mimicking what actually happens in the real world. I mean, maybe I use some kind of hypnotism to convince people their partners are having affairs, but that's not the way people naturally go about when they have that type of suspicion. That's not the way it naturally occurs. So I wouldn't be observing what naturally occurs in the real world. So experimental research, its key strength is we can use it to determine cause and effect, and especially we can use it to determine if treatments are effective. We can do a clinical trial and determine if a treatment is effective, and that's a key advantage of experimental research. And the key limitation is that it's often not the best research to use when you're wanting to explain the way things naturally occur in the real world. So we've been considering all the different questions that Moniz could have addressed if he had quantified his observations. We've been considering, for example, what if Moniz had administered the brief psychiatric rating scale? What are all the questions he could address? And we saw how he could address the question of, are these scores high or low? And he could address questions of scale reliability and validity. And he probably would have discovered that his assessments lack validity. And then just now we were talking about how we could do correlational research or experimental research. Now, in the case of lobotomies, which are a type of treatment, the most important question here would be whether or not the treatment was effective. And as I just mentioned, the type of study that will allow us to determine the effectiveness of a treatment is a clinical trial. So clinical trial, that's the type of experimental research that we do to test the effectiveness of a treatment. So we could ask, what if Moniz had conducted a clinical trial? So in doing a clinical trial, what additional questions can we address? Actually, as it turns out, the questions we can address when doing a clinical trial will be essentially the same types of questions we can address if we were doing correlational research. I actually have two more questions I want to talk about that we can address, and we can address both of these questions if we're doing experimental research like a clinical trial or correlational research. But in this case, the most important type of study to do would probably be an experiment, because the question is whether lobotomies are an effective treatment. So what if he did a clinical trial? So we have, say, for example, case 1, 2, and 3. These might be the cases you already talked about, the 3 cases that received lobotomies, or what he called leucotomies. And we have their scores on the brief psychiatric rating scale. So what if he did a study where he actually had 6 patients altogether, And what if he randomly assigned each of these 6 patients to these 2 treatments? So say case 1, 2, and 3, these were the people that were randomly assigned to the treatment group. And say case 4, 5, and 6 were the people randomly assigned to a control group. And so what if he did this, where he got 6 people were experiencing some kind of mental illness, and he randomly assigned 3 of them to get lobotomies and 3 of them to not get lobotomies. And then afterwards, he observed their scores on the brief psychiatric rating scale. And so here we have the scores of the people that received treatment, 27, 36, 54. And the people in the control group, they received scores of 45, 39, and 51. So in this case, so if Moniz has conducted this clinical trial like what we're looking at right here, what are additional questions that we could address and that we need to address? So if Moniz had conducted a clinical trial, one important question that we could address, in fact, we very much would need to address, is this: how big is the effect? And this is an important question to address regardless of whether you're doing a clinical trial or correlational research. In all research studies, you do a study, you get results, and you get some kind of an effect, and the key question you want to address is, how big is the effect that you got in your study? So for example, in our study here, if Moniz did a clinical trial and we have this treatment group, 3 people in our treatment group that had scores of 27, 36, and 54 on the brief psychiatric rating scale, and we could take these 3 scores and add them together and divide by 3 to get the average score. And in this class, whenever I take the average of something, I'll call that the mean. So the mean and the average are 2 words for the same thing, and I will usually use the word the mean. And so the mean of these 3 scores is 39, and the symbol for the mean, I'll use a letter X with a bar on top of it as a symbol, X bar. I'll call that X bar, will be the symbol for the mean. So in our treatment group, our mean score was a 39, and in our control group, the mean score was a 45. Now, this is just made up numbers here, but in my example, I actually have the treatment group better off than the control group, because if this is the brief psychiatric rating scale, higher scores mean you're having more symptoms. So we have our control group is having more symptoms at a 45, our treatment group is at a 39. And so we can say, what's the difference between our treatment group and our control group? And so the treatment group was a 39, control 45, so 39 minus 45, that's a 6-point difference between our 2 groups. Our treatment group was 6 points better off than the control group. Now, that still leaves us with a question. Okay, well, it's a 6-point difference, but how big is that? Is that a big, important difference, or is that a trivial, small difference? If we found a 6-point difference on the brief psychiatric rating scale, should we be enthusiastic and jumping up and down and super excited about this amazing, incredible, fantabulous, spectacular effect? Or should be thinking of meh or no? Is this kind of like, where are we on this scale? Is this a super exciting thing, or is this kind of like that's not hardly any effect at all, just 6 points, that's almost nothing. So is this a big effect or a small effect? And how do we decide that? And hopefully as you're looking at that, you'll realize this is a tricky thing to decide. Just to say there's a 6-point difference, it's not inherently obvious whether or not a 6-point difference is a big effect or a small effect. And so we'll be talking about ways that we can determine whether this type of effect is big or small. We'll be talking about ways we can address this question: how big is this effect? Is this something to be excited about or something not to be excited about? In fact, this is one of the major questions we'll be focusing on throughout the rest of the semester. The question of how big is the effect will be a key question this class will be all about. And now for the final question in this list of questions that Moniz could address if he had quantified his observations is here. So if Moniz had conducted a clinical trial, one other question that we could address and would need to address is this one: could these results simply be a random chance? So to what extent do these results reflect something true about the way the world really is? And to what extent might these results simply be a fluke, a random chance finding that would probably come out different if we did our study again? Are these results simply random chance findings, or do they reflect something true about the way the world really is? So in our study, we had a treatment group, and their score on the brief psychiatric rating scale was a 39. We had a control group. Their average score on the brief psychiatric rating scale was a 45. That was a 6-point difference. The treatment group was better off. They had fewer symptoms by 6 points. And so in this study, the treatment group was better off. Now, if this is just a random fluke finding, then maybe the next time I do my study, if I replicate this, we get another 6 people and randomly assign them to a treatment group and control group. Maybe the next time I replicate my study, I find the control group is better off. Maybe they're better off by 7 points. But then maybe if I do it again, it's the treatment group is better off, and maybe they're better off by 3 points. But maybe I redo it again, and next time the control group is better off by 12 points. So each time I replicate my study, I might get a different result. And if I'm getting wildly different results every time, then any one study that I'm looking at is simply a random chance finding. It's not telling me something true about the way the world really is. So when I look at these results, how much can I trust them as something true about the way the world really is? And how much should I look at them with suspicion, saying, well, these results could simply be random chance? Now, when you think about it, there's one key issue that's going to make a difference here. There's one key thing that's going to determine how much we might trust these results as reflecting something true about the way the world really is, and how much we should be suspicious about these results as maybe simply being a random chance fluke finding. So what would that key issue be? Well, one of the key issues here is going to be the sample size. And in this case, we only have 6 people. We have 3 people in a treatment group, 3 people in a control group, and with a sample of just 6 people altogether, that's not a very big sample. And so I would be rather suspicious of these results. If I had a much bigger sample, I could have more confidence that these results I get from a study might reflect something true about the way the world really is. But when your sample gets small, the smaller the sample, the more we get suspicious that results might be simply the result of chance findings. And this question about whether results might be random chance findings, how much results reflect just random chance, and how much they reflect something true about the way the world really is, this is a question we want to address both when we're doing experimental research and when we're doing correlational research. So this is a question that's important regardless of what type of research we're doing. And this is another question we're going to spend quite a bit of time on in this class, looking at the ways we can address that question. The question of, could these results be random chance? Anytime we do a research study, we want to address a question about effect size, how big are the results, and we want to address a question of, could these results simply be random chance? And a large portion of what we're going to be doing this semester is focusing on those 2 questions, the question of effect size and the question of, could these results simply be random chance? So, as I was saying, for most of our class, we will be focusing on these 2 questions. That is, if I do a research study and get results, one important question is, how big is the effect that I observe in my study? And another important question is, could the results of my study simply be random chance? That is, how much should I trust my results as reflecting something true about the world? And how much should I be suspicious of my results as something that could simply be a random chance fluke finding? And as we will see, we will address this question about the effect, which is actually a question of effect size. So the question, how big is the effect? We're going to address that question of effect size with something called a descriptive statistic. And we're going to address this other question, could the results be explained by random chance? We'll address that question with something called an inferential statistic. Now, at this point, you may be wondering, what do I mean by descriptive statistic and inferential statistic? Well, to explain the difference between descriptive and inferential statistics, I'll need to talk about just a few other definitions. So before we can define the terms inferential statistic and descriptive statistic, we need to first define these terms: population, sample, parameter, and statistic. What do these terms mean? So The population would be all the cases that you want to make some kind of claim about or that you want to learn about when you do a research study. So if I do a research study and I want to learn something about all the people in the world, and I want to be able to make some kind of claim about getting results that apply to all the people in the world, well, then my population is all the people in the world. Or if I wanted to do if I wanted to do a study where I test a treatment for depression, maybe in that case, I want to learn something about people who are depressed. I want to learn if my treatment is effective for people who suffer from depression. So in that case, my population might be all the depressed people in the world. Or maybe I do a study and I'm only interested in, say, children who are in elementary school in the United States. So in that case, my population might be all the children in elementary school in the United States. So the population is all the cases or all the people that you want to be able to make some kind of claim about or that you want to learn about when you do a research study. And of course, the key challenge in research and the key reason for needing an entire course on statistics, the key thing we're going to be addressing in this course is the fact that when we do a research study, we usually don't have access to the entire population. Things would be a whole lot easier if we did, but I can't do a study where I include all the people in the world, or where I include all the depressed people in the world, or even where I include all the children in elementary school in the United States. So what we have is I want to make some kind of claim about a population. My goal in research is I want to study the population and I want to make some kind of claim about the population. But when I do my study, I only have access to a sample. So the sample are all the cases that I actually collect data from in my study, the cases that I actually observe in my research study. So I want to make a claim about the entire population, but what I have is just a subset of that population, just the cases that are in my study, and that's my sample. Now, when I do my research, if I do have my sample and I calculate some kind of numerical value that describes my sample, I call that a statistic. So a statistic is a numerical value that describes something about my sample. Now, if I had a numerical value that describes something about the entire population, I'm going to call that numerical value a parameter. And so what this means is when I do research, what I really want to know, I want to know the parameter. I want to know the numerical value that describes something about the population. So for example, if I'm doing a treatment study for depression and I have some people who receive a treatment and some who are in a control group, I want to know in the entire population, what is the size of difference between the treatment group and the control group? That would be a numerical value that would describe the size of difference between the treatment group and the control group. And I really want to know what is the parameter, what is the true numerical value if I included all the people, all the depressed people in the world, what would be the true value of the difference between the treatment group and the control group? But I don't have access to the parameter. I can't get all the depressed people in the world in a study. Maybe have a study with maybe a sample of 50 people and that's all I have. So what I have is my statistic, the numerical value that describes what I observed in my sample. So a statistic is a numerical value that describes my sample. The parameter is the numerical value that describes the population. And the key dilemma we have in research is that we want to know the parameters, but we don't have parameters. Instead, what we have are statistics. We have the values that describe our sample, but what we want is the values that describe our population. And so with this, we can now look at the difference between an inferential statistic and a descriptive statistic. So note, these are both statistics. These are both numerical values that are derived from my sample. So an inferential statistic is where I get a numerical value that's derived from my sample. So it is a statistic, but it's a numerical value that gives me information about how well my results apply to the actual population. It gives me information about how well my statistic actually comes close to being that parameter. So the inferential statistic is a numerical value that comes from my sample, so it's a statistic, but it gives me information about how close my sample comes to the true population. And that's an inferential statistic because I'm trying to make an inference from the sample to the population. In contrast, a descriptive statistic is simply a numerical value that simply describes what I have in my sample. It doesn't give me information about how close my sample comes to the population. It describes my sample. So if we go back to those two big questions we're trying to address, if I wanted to address the question of, in my sample, how big was the effect that I observed? Well, that's a descriptive statistic. What did I observe in my sample? How big of an effect did I observe in my sample? That's describing something about my sample, and that's a descriptive statistic. Now, if I ask the question, could the results of my study be explained by chance? Could they be a fluke finding? Well, that's asking the question of how close my sample comes to the true population, because if it's a fluke finding, what that's saying is that my sample does not come close to the true population parameter. The true population parameter is one thing, but by some random fluke finding, I got something different. So the question of could my results be explained by chance can be reworded to say it's a question of how close do my results from my sample come to the true population? How close does my statistic come to the true population parameter? And that's an inferential statistic. So the inferential statistics are the ones that answer that question of could these results be explained by chance? And we use descriptive statistics to answer the question of how big is the effect size? Which, by the way, there's other types of descriptive statistics we might want to use. That's not the only thing that descriptive statistics can do, but in this class, that's the key type of descriptive statistic that we will focus on, is using them to address that question, how big is the effect size? So that's the difference between an inferential statistic and a descriptive statistic. And that completes everything for Part A of Unit 1.